Um, so I'll get straight into it. What are we talking about? Well, perhaps we should have used the term holomorphic combinatorics, but the terms, it's basically set now. Flagellé was very influential. His book with Sedgwick was very influential. It's the Bible of the field, I guess. And what we're talking about is analytic in the sense of analytic functions, complex function theory. Of course, there are lots of different ways that you could apply analysis to combinatorics. But this is what we're talking about here. So the basic idea is you're trying to count something. Usually you have some kind of recursively defined class of structures. You're trying to count how many there are of a certain size, and usually they have a recurrence relation, and you somehow solve these using generating function techniques. It's very much the analog of what you do for differential equations. You might introduce a Fourier or Laplace transform, solve that, somehow try to extract information about the original by inverting the transform. That's kind of the technique. So very classic, simple example that essentially, I guess everyone will be familiar with. You start off with a very simply recursively defined function. You introduce the generating function, which is just multiply formally by x to the n and sum. This was first done, I believe, by De Moivre around 1730, and it's been very fruitful. So once you do that, you immediately get a functional equation for the unknown generating function. And it happens to be a linear equation, and so you get a rational function. So it's about as simple as you could expect. Now that's the transform. You now need to invert the transform to find the original coefficients. So you're basically extracting the Maclaurin coefficients. One way to do that in the simple case is just partial fractions. Theta is the golden ratio. You factor the denominator, you use partial fractions, you use the fact that you have a geometric series, etc. You write it out, and you see that one of those terms dominates the other. It's much bigger exponential order than the other one. However, this method's very special, doesn't generalize much. If you have a function which is almost rational but not quite, you can't use it. So a better way to do it, which I won't go through in detail, is just to use standard residue theory. You know, we're talking about a function with poles, so it's a meromorphic function. Standard first, course in complex analysis will show you that Cauchy's residue theorem will also give you a way of evaluating an integral, and the integral is, if you set it up right, will actually give you exactly the coefficient. So that's sort of an alternate way of doing it. And that's the one that's going to generalize and will go to higher dimensions in a way that the partial fraction method will not. So the key principles of analytic combinatorics are basically find the generating function somehow. It's not always that easy, but I think of this usually as the easy part. You have a rational or maybe algebraic or somewhat nice expression for that generating function. Then you extract the coefficient using the Cauchy integral formula. This is a multidimensional version. Think about it in one variable. You're just integrating around a little circle around the origin. Then if you expand that circle out, you will eventually hit a singularity. And where that happens is, we call that, say, a dominant point, where you first hit one. And that determines the exponential growth rate. It's basically 1 over the modulus of the thing that you run into. And so that is general. Now, if you want to go further and have more precise estimate of what's going on, remember that in most cases, we're not going to be able to exactly get a reasonable formula for these things. We want to reduce to some kind of asymptotic formula. The type of the singularity that is going to make a difference, whether you have a pole or whether you have a branch point or an essential singularity, these kinds of things make it a big difference. But this kind of analysis has been done massively. Sedgwick's book is several hundred pages, and it does it all in great detail with huge amounts of interesting applications in the one variable case. However, when you move to several variables, when Robin and I started more than 20 years ago, there was basically very little there. There were several authors bemoaning the state of the field, because it's relatively easy to find the transform in closed form, but inverting it is hard. So even if you have a rational function, there is no such general partial fraction decomposition in several variables. Instead of having single poles, let's say, just isolated points that you do in one complex dimensional problem, you're going to get in general a variety. Okay, you have a rational function, let's say, where the denominator is equal to 0. That's a d minus one dimensional variety, and it could have arbitrarily nasty geometry. When you look at the complement of it, the topology is harder than it was in one dimension. You can do residue theory, but it's a lot more complicated. And everything in higher dimension is harder because it turns out lots of things scale exponentially in the dimension. Lots of things you would like to compute as part of your algorithmic computation of final results. Intermediate results can become quite large and complicated. So there's a lot of negatives there. To give you an example of a very simple problem, you suppose you're starting at the origin and you're doing walks where you can't go a negative in either coordinate. So you go into the nearest neighbor. You're only allowed 3 of the possible, I guess, 8 ways that you could go. And the recurrence you get for counting those number of walks that end in the point RS, which is necessarily in the positive quadrant, is given by this linear constant coefficient difference equation or recurrence relation. And it's easy from that to work out an explicit formula for the generating function. However, how do you compute an approximation to ARS for large R and S? It's not immediately obvious. If you only know one variable problems, you might be able to get it to work in this case. That's simple enough. But in general, these questions don't look easy. To give you an idea, the singularities of this particular problem, so the zeros of the denominator, in the positive orthant look like that. There are many other complex singularities. These are just the positive real, the real ones, actually. Sorry.
Mark, Seth has a question.
Oh,
he's
yes.
asking, what is the singular variety of a function? What do you mean by singular variety here? That's Seth's question.
It is the set of zeros of the denominator and if you have a rational function. That's the easiest way. Of course, we could be more general, but let's just think about a rational function for now. Just consider the set of zeros of the denominator. Those are singularities of the rational function, and those are things we have to deal with when we are going to try to evaluate the integral. We're going to run into them as we move the contour around. I'm going to need to do some kind of residue analysis, some kind of analysis.
Thank you.
Yeah. Thank you. So you can transform by putting x equals e to the u, y equals e to the v, and just look at the positive coefficients, the positive points here. And then if you transform that into UV space, the log space, it looks kind of like this, actually. And the yellow here is described going out to minus infinity. So that's like going to 0. That is describing the region of convergence. And then you have the boundary between the yellow and the blue. That's the boundary where the singularities are. And the geometry of this boundary turns out to be extremely important. So we'll come back to that. So I'll give you a big outline of what we are looking at here. We want asymptotics of...
another question, Mark?
Oh, yes.
Peter Winkler asks, aren't there 3 ways to get from R-1, S-1 to RS? Aren't there 3 ways?
Not, well, no. Yeah, well, there are, but we're just looking at if you think about the path and then you think about all of the path except for the last step, how many ways can you get to RS? You either get to R-1S or RS-1 or R-1S-1, and then you do one of the steps from the step set. That's all that's saying. I mean, there may be other recurrences you could write, but that's the most obvious one.
Thank you.
So we want asymptotics for large values of the index. It's a multi-index here now in general. So we saw dimension 2 before. It turns out that, in one dimension going to infinity, there's not too many ways you can go. R is going to infinity. It's positive. It's a positive integer. In general, though, you have a multi-index, so you have to decide where you're going, and you fix a ray for now. Let's just fix a ray that we're going to travel out along. Now, that sounds like a big restriction, but actually it turns out not to be. So I'll talk a bit more about that. And it turns out that by doing that, you can reduce the number of points that are actually relevant for your analysis down from this infinite variety, this d-1 dimensional set, down to just a finite set of critical points. And generically, for combinatorial problems, there's only one point that actually matters, and it's in the positive orthant, as it turns out. That's kind of nice. Then it turns out that based on analysis near that point, you can derive an asymptotic series. So basically, you reduce the integral to small integral near that point, around a little cycle near that point. Very similar to what you do in one dimension. And then it turns out there is an asymptotic series. It's a high-level overview, obviously, but everything is effectively computable from your initial data, just using derivatives and evaluating them at various points. And what you get, the important thing is that you get asymptotics. Now, I was fixing a direction, but now I can let the direction vary. And the nice thing is the error terms vary continuously because of the way we do this. And so you get what are called uniform approximations. So as long as you only move a little bit, if I wobble a little bit the direction and nothing changes in the geometry, I don't run into singularity of a different type, then my formula holds uniformly. The error terms, estimates and everything work nicely. So that is a big advantage of this method over any other method that you might run into. And there aren't very many, to be honest. So I want to just quickly run through, because a lot of you, well, some of you may have never seen any of this before. Some of you may have heard of it, and some of it's pretty old. So, we did the original stuff a long time ago, a pretty much bare hands calculation. We then tried to popularize it, but with examples. We derived a bit more complicated stuff. Then we had a SAGE package, and then we wrote this research monograph. And then we kind of sat back and thought, well, people will use this stuff. But to be honest, although it has been well cited and lots of people are using it, not as many as I think ought to. So that's why I'm going to talk a bit more about some more modern stuff that's going on. There are a couple of books which I think give a much easier introduction to the topic. So one of the original book is a bit tough in some parts, I think. I warned Robin that if we put too much Morse theory in it, it would turn people off, but yeah, he insisted. So we're revising that book, though, to come out within the next year or so, and that will be more user-friendly. It will have a lot more worked examples and SAGE worksheets and things like that. And Steve Meltzer, who's extremely active in the area, who's now at Waterloo, he is going to be helping out with that. We're running a math research community for late-stage grad students and early postdocs, which I spelt wrong there. That's been COVID delayed, but it's still going. And then also COVID delayed is the American Institute of Math in San Jose. They have a workshop that we'll be running next year. So just to tell you, if you'd heard about it and thought it was all old stuff, it is, but there's also a lot of new stuff going on. Right, I'll move on. Sample formulae. So what do those formulae look like? I said there exist these asymptotic formulae. Well, they look kind of like this. If you have a smooth formula, you can write a smooth point. So if you think back to the picture we had here, what you do basically in the generic case is if you want to have direct asymptotics in a particular direction, so think about just a direction going off to infinity and positive in both directions there. Think of a vector and stick it as a normal vector to that curve, a boundary curve between the yellow and the blue. You move it around, you move your vector until you until the normal vector is actually parallel to the what direction you want, and that's the point that controls everything. And analysis at that point, everything can be expressed geometrically. So it turns out you can express the formula in terms of, you've got the exponential rate, the p to the minus r part, and then you have the kappa, which is the Gaussian curvature at that point. So everything can be derived, can be described in a very nice geometric way. And all these things can be calculated just with first and second derivatives, although the formulas are a bit messy. If instead of a smooth point, though, we have something different, suppose we had D sheets, you think about even like D hyperplanes, if you like, all intersecting at a single point, down to a single point, then you get quite different results. Instead of having a single direction that determine where, instead of that point determining asymptotics in a single direction, it actually determines them in an entire cone. And that's because when you have a surface that's not smooth, you don't have a normal, the way I was saying before, a normal direction, you have a normal cone, which are the normals to the supporting hyperplanes of that convex set back there. And that's actually what happens. And you get quite a different formula. It's flashing past quickly. It's hard for you to follow everything. I know that. Just giving you the big picture of, we have different formulas for different geometries. And those are the two simplest geometries. And we don't yet know how to do everything, obviously. They can be arbitrarily complicated. So now going back to our Delanois walks that we have, that's the formula you get. I want to spend just a minute complaining a little bit. This paper, if you have a look at it, which I recommend not probably, it derives more or less this formula. And that would be okay, except, 10 years before we showed how to derive such a thing in general, and they're not using those methods. They're doing it by some bare hands method, reinventing part of the wheel, right? And that wouldn't have been so bad, except that I know these people and had talked to them and even given talks at conferences where they were in the audience, so they probably should have known that. But even worse than that, this very example was the running example in our first paper. So this is kind of, I just want to make sure that people, at least if they're not going to use our stuff, it's because it's not useful and not because they don't know about it. There's a huge number of problems that can be attacked using this methodology and are as simple as this one. There are a lot of harder ones as well, but these are the sort of really simplest cases. Just mention very quickly, if you've ever heard of the diagonal method, like in Stanley's book, doesn't really work. And I'm happy to talk to you about why later on. If you want to know numerical results and you plug in just into that formula I had, and suppose you want to know the 1319 diagonal for whatever reason, even for n equals 1, that expression gives you less than 1% relative error, and the error decreases nicely. And by taking more terms in the expansion, which isn't easy, I admit, it's quite a lot of computational work to generate the higher order terms, but once you have them, you get better and better approximations. So what can you do with these methods? You can do asymptotics, you can do numerical approximations. One thing I won't have much time to talk about is more recent work where we just, well, when I say we, Robin Pimentel and some collaborators, disproving some positivity conjectures, or at least showing how you might do it. The idea is that if your conjecture is that some sequence of numbers is ultimately positive, then if you can have an asymptotic approximation for it, which is eventually not always obviously positive, then you can't get a contradiction there. Right? So it's a necessary condition that the asymptotics should look positive. And if they don't, then that's a disproof. Limit laws, if you've seen this sort of thing, it will be clear, otherwise it's kind of vague. Let me just say, if you have a bivariate sequence, say ANK, sometimes if it's a counting problem, if you normalize it, you can think about it being the probability that xn equals k, where xn is a clearly defined random variable. And then you can look what happens for large n. And the generic behavior here is, if everything goes nicely, is that you get sort of Gaussian behavior, but there are other possibilities. Give you a quick example of the kind of thing we can do. This table here of asymptotics relates to a different type of walk model where they're confined to be in the positive quadrant. These are basically all the inequivalent cases of step sets in the pictures that you see there. And it turns out that all these formulas are correct, and they were all proved, essentially all of them, all but 4 of them were proved by Steve Meltzer and myself using a methodology that I've just been talking about. However, it was more tricky in this case because the hard part actually for us, since we knew so much about doing the asymptotics, really the hard part was deriving the generating function, which took a bit of work. But once we got that, everything eventually fell out with a lot of care. These numbers had been conjectured 10 years before by Boston and Cowers on the basis of a lot of numerical results, but there were no proofs of those. And you have to have pretty fine, you can see, if you want to get precise asymptotics, there's some pretty fine details of algebraic numbers in that right-hand column, and then you also have periodicity there at the bottom. So you have to be pretty precise. When I was preparing this talk, I thought, well, what would this audience might be interested in? And I just started randomly, well, not randomly, but I started looking in Google Scholar and thinking, are there anything? And I found 2 papers by Pamela Harris and co-authors, both with a representation theoretic flavor. So the first one is kind of a vector partition problem, and it has this generating function. Now you can analyze this and you very quickly get the Gaussian behavior that I talked about before, which is the result of one of these papers of Harris or whatever. They did it in a more bare hands manner. These Littlewood-Richardson coefficients are pretty interesting. And it turns out that there is a nice generating function for the square of them. And you'll see that it's not rational. It's an infinite product. Now, infinite products like this are famous in partition theory, but in one variable, they're really hard to analyze. But that extra variable gives us quite a lot of leeway, and we managed to do quite a bit with it. The exact same generating function came up in a problem where I was working with some physicists, string theorists. I still don't really understand the physics side of it very well, but it's the same generating function. So we managed to say some reasonably useful things about that. I'll give you one more example. The Narayana numbers, they count ordered, what I say there, rooted ordered trees by edges and leaves. But the nice, interesting thing about them is they're not a rational function, it's an algebraic function. But there's a really cool procedure, which is not as well known as it should be. But well, Safanov and various other people have used it as well, which enables you to lift it. So basically the coefficient you want, which is this ARS, you can write it as a, not quite a diagonal, but kind of a generalized diagonal of a bigger, higher dimensional function, which is rational. This is a general theme that the higher, if you increase dimensions and simplify the functional form, these kinds of things happen quite a bit. But notice it's not an actual diagonal. And so you need to have those kind of uniform asymptotics that I talked about before in order to be able to get nice results here. We can get results. There's a few tricks. The leading term asymptotic vanishes. You have to go to the higher order terms. But you get a lot of interesting things just from this one example. One thing is that we can go beyond rational functions. We can go to algebraic ones, so with square root singularities and things like this. The other thing that's kind of interesting is that this generating function has some negative coefficients in it, whereas the diagonal that we're looking at, the generalized diagonal, they're always positive because they're counting, these counting numbers. And that makes a bit of a difference, and in fact it makes it quite hard to work out what the contributing singularities are. And that's where a lot of the less pleasant topology can come in. This particular example, we can do it. In general, it's a little harder once you leave the combinatorial realm and have negative coefficients. The other thing is that if this is a 2-variable problem and we go up to a 3-variable problem, if you are stuck in the univariate world of only thinking about 1-variable problems, it wouldn't necessarily occur to you to lift from 2 to 3, right? You might think, well, it's a 2-dimensional problem, let's slice it somehow and go along array and what I was talking about before. That really isn't going to work well, as it turns out. And so adopting this multivariate approach has been fruitful in this way, in a way that probably other people who were working on it wouldn't have been able to do. In other words, there were some natural things to try once we were in that realm, which other people wouldn't have tried. I've got one more example. How much time do I have? Negative or not?
You got 3 more minutes.
Okay, good. So here's just a very quick example. This is a made-up example. It's combinatorial problem. So 1 over h that has positive coefficients. It's the solution to a linear constant coefficient recurrence relation you can write down. I don't know any combinatorial meaning. I just made it up. It's an irreducible polynomial, as it turns out. And you have to factor it locally and not globally in order to find the sort of tricky singularity structure there. But it turns out to look like this. That's what the real points look like of the singular variety. And so this point in the middle, this double point, turns out to supply asymptotics in an entire cone. I mentioned that cone stuff before. And all the other directions you want come from appropriately chosen smooth points. But the formulas are totally different. So you get this sort of n to the minus a half behavior outside this cone, and inside the cone you get 6 plus exponentially small error. It's just really, really precise. And on the boundary of the cone you get 3, which is a half of 6. And depending on the speed at which you approach the boundary of the cone, you can get all kinds of weird stuff, which is hard. These phase transitions are very difficult to work out. So, you know, you can see there's quite a lot of subtlety, even in a relatively simple thing that I just wrote down like that. Some harder applications we have an idea how to do, except for the last one where I don't know how to do it. You can deal with the point where there's more than one contributing point. You tend to get periodic behavior. Quantum random walks are a great example. There you tend to get, instead of just isolated singularities that contribute, you get an entire torus full of them. But luckily the form of the generating function is nice enough that we can deal with that. There are these more tricky singularities that look like locally like a cube, like a cone, sorry, like a quadratic cone, rather than nicely intersecting hyperplanes or just a single hyperplane that we had before, so more complicated geometry. But some of those have been done. And I say the last one I don't know how to do, but it's a fascinating problem involving the random walk on specific types of lattices and the return probability to the origin. Yeah. So that's it. Those are the books I mentioned. There's the website. And I leave you, as I always do, and impinge on your time with my overtly political slide, and then I will be seeing you back in Gather for the questions.